Hi everybody, I'm Soma Datta and my co-author Sunitha Palissery. We both have worked on a project called Uncertainty Aware Seismic Signal Discrimination using Bayesian CNNs, and I'm going to present it now. So I'll start off with an introduction, give you some background, then we'll move on to methodology and then discuss the results and I'll tell you the conclusion. So the real problem that we are trying to solve is that seismic signal classification is essential for early detection of earthquakes as well as monitoring seismic activity, because this is connected with a lot of uh, uh, early forecasting and risk mitigation activities. So one of the crucial challenges in seismology is seismic signal classification. If you know if the approaching waveform is a quake or just simply a noise, you can quickly take action and save lives, potentially save lives. So the problem that we were trying to tackle, the specific problem that we were trying to tackle was the complexity of seismic data makes it difficult to correctly classify quake and noise waveforms. So this is because seismic signals exhibit diverse patterns and characteristics because they're geological phenomena, and even man-made activities can sometimes result in seismic waves that are difficult to classify because they show very similar characteristics to quakes. So, and traditional methods, as in the existing methods that are there to uh, do seismic signal classification, often struggle with signal variability, noise interference, and limited label data, uh, and often provide deterministic outputs. So by deterministic outputs, I mean they do not give you a confidence score or an uncertainty estimate in their prediction. So it is deterministic. So they either say that it's a quake or it's just simply a noise signal. And in these illustrations, you can see this is an earthquake waveform. You can see that it has some distinct characteristics of its own. And this is a noise waveform. It looks completely different from earthquake waveform. And given if, say, a traditional CNN, or if a traditional convolutional neural network is given these two images, I'm guessing it will easily classify this into a quake waveform and this into a noise waveform. But say it gets something like this, it may find it difficult to classify this waveform, and even if it classifies, it will just tell if it's a quake or noise and won't give you how confident it is in its prediction. So this is a quake waveform, but as you can see, it closely resembles the characteristics of the noise waveform. So that is what the problem, that is the problem that we were trying to tackle in the area of seismic signal classification. And now moving on to why, instead of deterministic, why do you want to know how much uncertainty is there in the prediction? So like, why does uncertainty matter when a model is predicting? So in high stakes fields like earthquake monitoring, understanding uncertainty can reduce risk of false alarm and increase trust in model prediction. So uh, let us take a simple example. I'll take a very simple example to kind of explain explain why uncertainty matters. Say you and a friend are hosting an outdoor event. You plan to host an outdoor event in the evening, and you consult a machine learning model saying that uh, what is the probability? Is it going to rain in the evening? That is what you ask it. Is it going to rain in the evening? And it is a forecasting algorithm, and it will give you an output saying ki, yes, it is going to rain, or no, it is not going to rain. So when you ask that question and it gives you an output, say the output is it is going to rain in the evening, but then you want to be sure as to it'll rain or it'll not rain, because you have to make arrangements and arrangements are costly. So you want some sort of confidence in the prediction uh, when it tells the that it'll rain in the evening. that is where uncertainty matters. So say you ask it, okay, with how much probability or with how much confidence do you think it'll rain? And if the model simply shrugs its shoulders saying, ki, I don't know with what probability it'll rain. I just made a prediction, that's it. That is not really helpful because it's not really telling you what the model uh, has seen or how with how much confidence the model is actually telling you uh, the prediction. So that is why uncertainty matters. Like when you give a prediction, you want some confidence score on an or an uncertainty estimate along with the prediction. So moving on, that is the example. So similarly, when it comes to earthquake monitoring, you want a model that can give you a confidence score, not just a prediction saying ki, yeah, this is an earthquake. You also want it to give you a confidence score because this will actually increase your trust in the algorithm. When the algorithm is doubtful, but yet it gives a prediction, you don't want that. So that is why uncertainty matters, uh, especially in like high stakes fields, like medicine or earthquake monitoring, where lives are at stake. Uh, Lives depend on one single prediction from a model. You want uncertainty quantification in those scenarios because you want additional information about the prediction. So that is why uncertainty matters. Moving on, and one more factor is seismic signals are really complex because they are geological phenomena and they emanate from Earth as well as man-made activity. Man-made activity can be either mining and windmills. These all create seismic signals, and these can easily be mistaken for earthquake activity instead of man-made activity. So they the seismic signals exhibit inherent variability in morphology, amplitude, and noise characteristics, making them challenging to classify accurately. And conventional classification methods actually struggle to accommodate this complexity and often overlook the nuanced uncertainty present in the data because uh, by nature, the geological phenomenon are uncertain. That is why uncertainty matters. So this is one illustration showing how predictions without uncertainty and with uncertainty. So say this is the curve, like the fitting curve of a model, and this is one prediction point. So say you give it an X value, it'll give you a corresponding Y value. So when there is no uncertainty quantification in the model, it'll give you a deterministic value, it'll give you a single point. Okay, but when say there is some uncertainty, say for these values of X, the sorry for these values of X, you can see that the uncertainty is high and the output can lie anywhere in this range. And similarly for uh, these X values, you can see that there is an uncertainty window. You can not be deterministic about the output. So the model is not equally confident in every prediction. So for every value of X, the model is not equally confident. And we need to know when the model is uncertain in its predictions. So if the model is uncertain for certain values of X, we need to know that, okay, for these kind of signals, the model can't not accurately, model can't confidently classify the signal. Now, so what is the solution to having uncertainty quantification in your model? That is where Bayesian models come in. So to tackle uncertainty in seismic signal classification, we move beyond traditional neural networks to Bayesian models. So Bayesian neural networks provide a principled approach to quantifying uncertainty in neural network predictions by modeling uncertainty as a distribution of over model parameters. This stands in contrast to the traditional neural networks, which use fixed parameters, where point estimates that is fixed parameters are used. So I have included a small diagram. So this is a traditional neural network. As you can see, the model parameters, that is the weights of the model, are fixed. But in a Bayesian neural network, the weights of the model are actually not fixed weights, rather they are distributions. These distributions can be Gaussian or any distribution that you choose. I mean, the distributions you choose will impact the accuracy as well as other metrics of your model. But yeah, you choose distributions rather than fixed weights in Bayesian neural networks. We'll now explore what Bayesian inference, how inference happens in Bayesian models, types of uncertainty, and how Bayesian CNN work. So Bayesian inference essentially uh, follows Bayes' theorem. If anyone is familiar with Bayes' theorem, they know that you can, given a certain evidence and likelihood and the prior, you can calculate the posterior. So what this means is it incorporates prior knowledge. So you have uh, data and you have prior knowledge, that is beliefs before even seeing the data, and then you have data. So when you have data as well as some hypothesis about what will be the posterior given the data as well as the evidence, you can use Bayesian inference to form a posterior distribution. So Bayesian inference uses prior knowledge in the form of a prior distribution in order to estimate posterior probabilities. So the model updates its beliefs after observing new data. So the posterior represents how we revise our prior beliefs in light of new seismic data. So the flow is usually like you have a prior distribution that you set for the Bayesian model, and then you have training data, and then you give it likelihood. Likelihood is how probable the outcome is, given that I have chosen this prior and this is the data. So Bayesian CNNs essentially use Bayesian inference. So instead of having fixed weights, as I've said, BCNNs treat weights as random variables with distributions. This captures epistemic uncertainty, which we'll discuss more about later, reflecting the model's uncertainty about the best weights to use. So since these weights are not fixed, rather they are distributions, you are incorporating uncertainty, which will allow the model to capture uncertainty in its predictions. That is how, in one line, Bayesian CNNs work. By using a distribution instead of a fixed parameter, BCNNs express uncertainty in their prediction, and this will lead to improved decision making in uncertain seismic environments. Training BCNNs. So to train a BCNN, you update the posterior distribution over weights during training, reflecting the model's learning process. So over the training, over the number of iterations, the training iterations, the model continuously updates its posterior distribution, taking the prior into account, the prior distributions as well as the random variables that are being used as the weights into account, and it updates the posterior distribution by calculating loss similar to a normal CN. So to achieve the weights being random variables with distributions, use special layers, which are called convolutional 1D flip out layer and dense flip out layer. And these layers are from the TensorFlow probability library. These can help you implement the weight being a random variable with distribution. So these layers are based on flip out estimator. So what a flip out estimator does is it efficiently estimates the gradients of stochastic weights by leveraging reparameterization tricks. We'll discuss more about this later in the coming slides. And now I'll move to the ability of BCNNs to incorporate uncertainty, makes them more resilient and trustworthy for seismic monitoring. This is because when you have, a model that can express uncertainty, you can be more confident in making the decision, because now you know that the model is actually certain of its prediction, and this will allow you to take your action more confidently. So that is why using Bayesian CNNs, it is a more resilient and a trustworthy approach to seismic monitoring, especially in low SNR cases. By this I mean especially when the incoming signals that are picked up by the model have a low signal to noise ratio. When the signal is almost blurred out by the noise that it is carrying, it makes it hard to distinguish. And in those cases, if you have a Bayesian CNN in place of a traditional CNN, the uncertainty that it gives you, the uncertainty estimate or the uncertainty quantification that it gives you, will make the prediction of the algorithm more trustworthy and more adaptable to real world scenarios. If it says that if it says that it has low confidence, then you can be more cautious and uh, reach out to uh, different sources of data to confirm whether it's actually a earthquake signal or a simple noise wave. So types of uncertainty. We know that BCNNs do uncertainty quantification, and there are essentially two types of uncertainty that they quantify. So one is the aleatoric uncertainty. This uncertainty results from inherent noise in the data. So as I said, seismic waves, they are very noisy, like because they come out of they are a result of complex geological phenomena. So the inherent noise in the data uh, will of course contribute to some uncertainty in the model's prediction. So this noise can be in the form of sensor noise or even environmental factors such as heavy machinery moving around, heavy trucks driving around. Even these contribute to noise in the waves that the model picks up. This uncertainty cannot be reduced but can be quantified. So as I said, it's inherent. So the noise is inherent. So you can't essentially wipe out this uncertainty. You can't reduce this uncertainty. It always depends on the data that you have, the training data that you have. If your training data is very noisy, then your uncertainty, the aleatoric uncertainty will be high. And even perfect models can't resolve this uncertainty due to this fact because it's data independent. So you may ask, okay, for example, aleatoric uncertainty is higher in low SNR environments. So for low SNR signals, when the signal is almost crowded by the noise, it becomes difficult to distinguish between the noise and the signal. So this results in a very high aleatoric uncertainty because of the noise. And next we have epistemic uncertainty. Epistemic uncertainty is not a result of the noise in the data, but rather it is due to the training data, rather the variation in the training data. If you have uh, only one type of events in your training data, your epistemic uncertainty will be high for other type of events when it encounters them in the test data set. So epistemic uncertainty is model dependent. It is how the model is trained that will determine the epistemic uncertainty of the uh, classifications on the test data set. This is uncertainty resulting from the lack of knowledge or insufficient training data. And this uncertainty can be reduced. Unlike aleatoric uncertainty, this is more within our control because given more training data, more diverse training data, you can actually reduce epistemic uncertainty. And so essentially, as these both uncertainties uh, are quantified, can be quantified using BCNNs, this dual handling of uncertainty makes BCNNs highly reliable for trustworthy seismic classification. Let's move to the methodology. So the data that we used to train our BCNN was from the SCEDC website. So the dataset comprised of 6-second long waveform snippets that had three components to them: the N, the north, east, and vertical components. And we had around 100,000 earthquake records and an equal number of noise records for the training. And the dataset was split into 80:20 ratio, which is standard. And one thing to note was that we made sure that the earthquake events that were in the test dataset did not did not be in the trained dataset. So all quake events belonging to one earthquake event will be classified either in train or test. We didn't have uh, one earthquake event having two different waveforms in the train and test data set. We ensured this separation because it will ultimately affect your validation because if your train and test are similar, it will of course create overfitting and other issues with your model. And this diagram highlights the area that was taken into consideration, the area in which the seismic waveforms and the noise waveforms were uh, taken from. Next, we move to model architecture. The architecture comprises of three convolutional layers, two fully connected layers, and an output layer. So the convolutional layers are 32, 64, and 128 neurons respectively, while the fully connected layers are 80 neurons each. The output layer has two neurons corresponding to the two classes, which are quake and noise. And the filter width used was 16. The activation function used was ReLU to reduce non-linearity. And the fact to note about this architecture that essentially makes it a Bayesian architecture is that the first layer that was used in this convolutional layer was a flip out layer. It was con 1D flip out layer that was used as the first layer. And the last layer was a dense flip out layer. Essentially, by adding these layers, we make the model a Bayesian model rather than just a simple convolutional neural network. By addition of these layers, it is now a Bayesian convolutional neural network. So this helps the model capture uncertainty in its predictions. So the way the convolutional 1D flip out layer works is it samples weights during training in a way that doesn't increase variance too much. So essentially, as I was talking before, this is what flip out does. This is how flip out works. The reparameterization tricks. This is what it does. It doesn't increase variance too much while sampling the weight. And it does this by sampling a random noise for the forward pass and correcting this based on the backward pass. So as I said, this is how it trains. So the Bayesian inference is that the forward pass is done by sampling a noise, but this is also corrected on the backward pass, and this ensures the variance of the gradient stay low, leading to a better and more stable training. So similar to the convolutional 1D flip out layer, the dense flip out layer also leverages flip out to improve variance reduction during the stochastic variational inference. So this is the loss equation that we followed. So the BCNN that is trained using stochastic variational inference, getting the approximate posterior of the weights. And the loss function used combines the typical classification loss. This is the typical classification loss, as well as a regularization term for the KL divergence. The Pellback-Leibler divergence is also included because this allows the model to generalize well, because as I said, seismic data is inherently complex and noisy, and you find a lot of various patterns. You want it to generalize well, so that is what prompted the inclusion of a regularization term in the loss function. And the total number of trainable parameters was, it was 5 million. Yeah, 5 million, around more than 5 million, and the model was trained for 40 epochs, and the batch size used was 48. So after the training, the results that we obtained were very good. In my words, we had an accuracy of 99.1% on the test set, and it was noted that for most cases, the model assigned a high probability to its predictions. It was, close to 1. So it predicted with very high probability, be it quake or a noise. It gave a high probability for most records. This is how the training curves looked. As you can see, it was minimal up till 1 point, and around the 18th epoch, we had convergence and accuracy increased and loss decreased. One more crucial evaluation metric that we used was the precision recall trade-off. So precision is the ratio of true positive predictions to the total number of positive predictions made by the model. So it measures how many of the predicted positive instances are positive. And recall is the ratio of true positives to the total number of actual positives. So this is, it measures how many actual positive instances that the model was able to identify. So in seismic monitoring, particularly for detecting low magnitude events, the balance between these both becomes increasingly crucial because say you prioritize precision. The way precision and recall work is if you increase precision, your recall falls. If you increase recall, your precision falls. So there is an inherent trade-off always between precision and recall. So say you prioritize precision and you set a high threshold, you set a very high threshold. Then you reduce false alarms by classifying only highly certain signals as earthquakes. But since your threshold is so high, since you said that only if you classify it with more than 90% probability, give me a positive signal, give me a signal that says that it's a quake signal. Because you have done that, you risk the omission of low magnitude events. As I was saying, the low magnitude events, which are essential for understanding seismic patterns, because usually these low magnitude events serve as precursors for larger and larger upcoming events, larger magnitude upcoming events. So it is crucial not to miss them and detect them early so that you can prepare for a larger event ahead. And say instead of prioritizing precision, you rather emphasize recall. You'll identify more potential events because now your threshold is lower. You will catch more potential events, but you also risk increasing false alarms. This is because the threshold is so low that even a false signal is able to uh, is able to trigger a signal from the model. So choosing the correct threshold becomes very vital when actually considering it in the operational seismic networks, considering the operational needs of the seismic networks when it's put in the real world, it becomes very crucial to choose the correct threshold. So now, after we calculated various metrics such as uncertainty, the precision recall as well as the accuracy, we moved on to uncertainty modeling, which was our primary goal. So uncertainty analysis was done post-training by generating multiple Monte Carlo samples. Used, to be precise, we used 100 Monte Carlo samples for each prediction. And the trained BCNN model uh, capture the uncertainty inherent in the model's parameters and architecture and obtain a distribution of the predicted probabilities for each class. So the way we do this is essentially we generate percentiles, the 2.5th and the 97.5th percentile of the predicted probability distribution for each class. And these percentiles serve as bounds for the epistemic uncertainty associated with the model's prediction. So these are generated by multiple Monte Carlo passes over one prediction, and uh, over the predicted probability distribution, we uh, calculate the percentiles, namely the 2.5th and the 97.5th percentile. And these 2.5th and 97.5th percentile serve as your bounds for the epistemic uncertainty. So as you can see, this is a quake waveform, and this is the uncertainty visualization, that the uncertainty estimate that was given by the model. So these are the 2.5th and the 97.5th percentiles for each class. And as you can see, it correctly classified it as a quake because it has assigned a higher probability to quake and a lower probability to noise. So there is a little uncertainty in its prediction, but it has given you that, with a very high probability that it's a quake. So next. Epistemic uncertainty, what we have observed is higher for ambiguous or complex waveforms, because essentially these waveforms weren't present in the training dataset. And when it comes to aleatoric uncertainty, it is more pronounced for data points that are class boundaries. That is when the waveform shows characteristics of both the quake as well as the noise, you have a higher aleatoric uncertainty. So seismic waveforms with low SNR show elevated aleatoric uncertainty. This is because they show characteristics of both the signal, they show both the characteristics of the quake as well as the noise. And high SNR waveforms have low aleatoric uncertainty because you have a stronger signal there. So that is what the model picks up and classifies it well. But it may still exhibit some epistemic uncertainty due to insufficient training data. So even this is what we have observed. So even if it's a high SNR waveform, high signal to noise ratio waveform, but it was not encountered in the training data, then if that kind of waveform was not encountered in training data, then it showed a higher epistemic uncertainty. So for example, take this waveform. This clearly shows the characteristics of an earthquake. You can see the dip as well as the rise, and this is clearly an earthquake waveform. So you can also, that is reflected in the model's prediction. It gives a very high probability to the quake class, essentially classifying it with very little uncertainty, saying that, yeah, this is definitely a quake waveform. So this will, really improve how the models are adapted into real world scenarios. Now look at this waveform. This waveform is actually a noise waveform, but it's showing some characteristics of the earthquake waveform, because if you see the other components, the E and Z components, they show similar disturbances to the earthquake waveform. And as a result, you can see that the quake class got assigned a significant probability of around 50% probability, despite this being a noise waveform. It still assigns a high probability to noise waveform, but you can see that it has also assigned a significant probability to quake. At the same time, you'll notice that the percentiles, the 2.5th and the 97.5th percentile, which represent the epistemic uncertainty, are also very high. This is because these kind of waveforms were not encountered in the training data. So by this, you can tell that, whenever a model predicts, you can know, okay, the model actually does not know these kind of waveforms. If the epistemic uncertainty is high, you know that the model doesn't know how to classify this waveform. So this really is the crux of having uncertainty quantification. By knowing what your model doesn't know, you can be very confident in the prediction that it has given to you and take action using that prediction. If the model says that it doesn't know, but still it gives you a prediction, you can consult other sources. But say it gives you a prediction with very high confidence, you can go ahead and take action based on that prediction. So as I was saying, the description is, for this figure, the description is essentially the prediction of a noise event with a high level of uncertainty, both epistemic shown by this longer bar, as well as aleatoric, as I've said, because this is due to the higher probability that is assigned to the wrong class. So what does this uncertainty quantification, how can this be applied in our real world and our day-to-day life? So uncertainty quantification improves the reliability and interpretability of models in seismic event classification and mitigation. Due to the uncertainty quantification that it provides, it is more reliable when compared to a model that doesn't give you any other info other than just a quake or a noise. It makes it more easier for the uh, seismic, for the earthquake decision makers, if they have to act or not act on a signal. So it enhances early warning systems by assessing prediction confidence and reducing false alarms or missed detections. It also helps the emergency response teams prioritize action based on prediction certainty. And this can actually help optimize resource allocation. So if there is one area that gives you, high uncertain predictions with very high uncertainty, you will optimize less resources there. And if say there is another area that is giving you predictions with high certainty, you will allocate more resources there, thereby optimizing your resources better. And this can potentially help save lives in the chance that there is an earthquake event happening. And apart from seismic event classification, even in industrial context, it mitigates the risk from induced seismicity. As I said, man-made activity can also generate some induced seismicity. So such as mining and heavy machinery moving around, all these the things that are considered under industrial context, these can be mitigated. You can understand that, oh, the model is giving an uncertainty estimate, a higher uncertainty estimate, because of these industrial activity going on. And you can talk with the operators of the industry to adjust the operations based on the uncertainty, so that you may not miss an actual earthquake event just because of this industrial activity going on, and that is creating some induced seismicity. So you don't want to miss an actual earthquake event. So you can talk to the operators and adjust the operations based on your uncertainty estimates. This also improves seismic hazard assessment, data quality control, and post-event analysis by addressing data gaps. As I've said, if you continuously notice epistemic uncertainty to be high in your predictions, that means that your training data has a lot of gaps. It has not considered various kinds of waveforms. It has not considered various kinds of characteristics that the model looks for in the waveforms. So this uncertainty quantification can also help improve your data gaps, or help address your data gaps. And in conclusion, the key takeaways are that BCNNs are capable of classifying seismic events with prediction accuracy of 99.1%. And the main strength of a BCNN is that it not only gives you a high accuracy, but also the valuable uncertainty estimate, which improves the reliability of the classification. And it also gives you an uncertainty quantification, which is the visualization of the uncertainty bounds, as we have seen. And this provides decision makers with qualitative insights, and this will help them, take informed decisions in seismic event classification tasks. And as I've said, it'll also help the emergency response teams and resource allocations. Also, the proposed BCNN model is easy to implement. As I've said, there are already existing libraries. TensorFlow Probability already has APIs. It has the flip out layers already implemented. So you can easily plug them in, and it's easy to implement in decision-making process in the earthquake monitoring, assessment, and possible mitigation, and help foster resilience and preparedness in earthquake-prone regions. Yes, that is my